These are the remaining topics for DC circuits. Some we've already covered, some we're talking about today in Lecture 14, and a couple of them we'll finish up in Lecture 15. And once we've finished this, we'll start on our next unit, magnetic fields and forces. We'll start off by talking about EMF and internal resistance of a battery or any DC power supply. EMF stands for electromotive force. That's an antiquated term that we don't really use anymore, but we still use the initials EMF. EMF refers to the maximum potential difference a power supply or battery can produce. Up until now, this symbol I've drawn stands for a battery or a DC power supply, but it stands for an ideal battery or DC power supply, which means there's no internal resistance. If a power supply or battery has no internal resistance, the voltage across the terminals will always be the same, regardless of how much current the battery is flowing. That's not true in the real world. Let's take a look at what happens if the battery has some internal resistance. Here I've drawn a battery that not only has a source of potential difference inside of it, it also has some internal resistance. The script E stands for EMF. That's the maximum potential difference this battery can produce. That's the labeled voltage on a battery. If this is a 1.5 volt battery, the maximum it's going to produce is 1.5 volts. If it's a 9 volt battery, the EMF of the battery, the maximum we're going to get from that battery, is 9 volts. The real potential difference we get from the battery is called the terminal voltage. Where we hook up our wires to the battery, what's the potential difference there across the terminals of the battery? It's always going to be less than or equal to the EMF of the battery, the maximum the battery can produce. Why is that? Because the terminal voltage, as we move through this battery in the direction of the current, we drop by the potential difference across the resistor inside the battery, R internal. We drop by IR, and then we have a potential gain through the EMF source, and then we come out the top terminal of the battery. So we rise by the EMF of the battery, but we drop by I times R, where R is the internal resistance of the battery. So if this was an ideal battery with no internal resistance, the terminal voltage would always equal the EMF of the battery. But as soon as we give it some internal resistance, as soon as we make it a real-world battery, the more current we flow, the bigger the delta is between its maximum voltage output and what we actually get out of the battery to drive our circuit. The more current we flow, the bigger the deviation is, because we're subtracting IR from our maximum value. That means in order to measure the actual EMF of the battery, current cannot be flowing. Here's a circuit diagram very similar to the ones we've been looking at up until now. Our symbol for the battery or DC power supply is for an ideal battery, no internal resistance, and it's driving current through two resistors in series, R1 and R2. But if we want to take into account the effect of the internal resistance of the battery on this circuit, we can just add another resistor to this circuit equal to the internal resistance of the battery. The actual battery is this dashed line. It incorporates both the source of potential difference, the EMF source, and some internal resistance. And the terminals of the battery would be here. So we can take into account things like internal resistance of a battery or a power supply, resistance of a wire, just by adding another resistor to our circuit diagram equal to that resistance. Here's an image from the end of chapter problems in our OpenStax textbook. You can see that the dashed lines indicate a real-world battery with some internal resistance. They've indicated that the EMF of the battery is 18 volts by using the script E. And they're using lowercase r's in this circuit diagram for all the internal resistances of the batteries. In this case, we have a 0.5 ohm internal resistance and an 18 ohm EMF for battery 1.